Welcome to a new video. Today we're going to introduce the notion of convolution. Convolution is an operation between two functions, and it's actually the convolution integral is something super important. It will be extremely important for your signal processing. It will be extremely important for the Laplace transform, also even more important for the Fourier transform. And it's something that you will learn now. I think it's the first time you ever see it, but hopefully will be helpful in all your engineering life. All right. So what is it? First, let's see the definition, the cold hard definition, and then we'll get some understanding about it. The convolution integral, also called convolution, sometimes convolution product, is of two functions, f of t and g of t. It's a new function that we denote f star g. So this is the convolution between the two of t, a new function of t, and it's defined as, that's the definition, the integral from minus infinity to infinity of f of eta g of t minus eta d eta. Of course, I can ask you, how many variables are there on the right? The answer is just one. Eta is not a variable, it's a dummy variable. It's integrated over. I could call it eta, or I could call it Joshua. I could call it Joseph. I could call it T prime. I could call it whatever, right? It's just the name is integrated over, I don't care. Okay? Super important. Anyway, what is the physical meaning of this? Well, this thing is a correlation function, and it kind of tells you how the shape of one function is modified by the shape of another. Have you ever heard about when you add a filter that is a Gaussian noise and then adds noise to a picture and things like that? This is why you do it. You're doing the convolution between the picture, your function that defines the picture, and a Gaussian function, things like that. Gaussian blur, that you would call it. Anyway, there are many ways of understanding the convolution. Let me give you some intuition. You will develop more as you study it in your signal processing. But just to give you an idea, you don't need this to use it to solve problems, but let me give you a little bit of an idea of what it is. So imagine that I have two functions here, f of eta, or f of t, you know, is Joshua, so why not t here, and then a g of t, actually g of minus t. I'll call it eta, just to not confuse you too much. I mean, I want to get you used to things not really to have the same name, but I call it eta. So this is f of eta, this is g of minus eta. And you can ask, are these two functions the same? Well, one way of checking if they're the same is what is their overlap. For example, imagine that I define this integral, f of eta, g of minus eta, d eta from minus infinity to infinity. What is this? Well, this is the overlap. In this case, this function is non-zero only here. That's the support of the function. We call it support. The set of points where the function is non-zero. Anyway, the function is non-zero here and zero everywhere else. This function is non-zero here and zero everywhere else. Now, of course, the overlap between these two functions as drawn here is zero. They don't overlap, right? If I compute the area under the product of the two, here is 0, 0 times 0, 0 times 0, 0 times something. Times this height, let's say it's 1, 0 times 1, but 0 because this function is 0 over here, and then 0 times 0, 0 times 1, then 0 times 0. So the overlap between the two, they don't overlap, so it's 0. Of course, if the functions were to overlap, imagine that g of minus eta would be something like that. Well, there is some overlap, right? So here you get the area under the product of the two in this region. That would be the result of that integral, the overlap between them. But as I wrote it, there is no overlap. Now, the question I would ask you is like, well, imagine that I hit a drum, bong, or a gong, bong, and then I wait for a long time, and then I hit it again, dong, and it's the same freaking sound. So your brain received the first sound, and then after many units, after a long time, your brain will receive another sound. If you compare their signals mathematically, well, they're not the same because one happened before the other. They don't have any overlap. But your brain does. Oh, hold on. I remember that signal. When it arrived, the first one, I can store the information, compare it with the second one. And they're the same. So you see, it's not because they're spaced in time, they're different, right? So a way to account for that is like, well, how about I displace this, you know, the amount of time that it took for me to receive the signal. How do I displace it? Well, add a plus t. If I add a plus t here, it's displacing that if I add a plus, so if this is g of eta, this would be, imagine I put it here, is g of minus eta plus t, which is what I have here. So the plus t is displacing the signal by t units. So the convolution, instead of this would be the convolution as I wrote it, f convolution g at 0, right? T equals 0, that's what you get. But if you instead do f g at, let's call it t equals L, where L is this distance, okay? At L, then I get that this is the integral of f eta g t minus eta, so L minus eta, the eta, and this is the full overlap of the function, the overlap of the function. So you see the convolution product is like, what is the overlap of the functions? But if I move, I want to be able to move one of them because maybe they're just the same, but they look different because they're far apart, kind of thing. There's a little bit of intuition about what the integral means. If you still have questions about it, which I hope you do, let's discuss it. I don't expect you to watch a video of me telling you and just being enlightened as if the Holy Spirit shed light on you or something like that. I'm certainly not divine. So please, come and ask questions, all right? I really want you to ask questions. That's the whole point of like stupidly attempting jokes that don't work. I mean, I'm not seeing your faces, so my jokes would be below par, of course. They're already bad. Imagine without an audience to actually look at your faces like, what is this guy saying? That helps me a lot to improve my jokes, and I don't have that. Anyway, I really hope that we got a little bit of intuition on that, and if not, we will discuss it. But let's understand now the math behind it. Oh, why do that? All right, so one of the things to realize, again, I said it already, this is a function of t. It doesn't depend on eta or whatever variable. If I want to call this something different, let me just call it something different. Eta prime, for example, g of t minus eta prime, the eta prime is the same. And if I call eta prime Joshua, same thing. This thing is just a function of t. All right, first thing, the convolution is commutative. That is not obvious, isn't it? Because it looks like the second one, you know, in the first one you do eta, and the second is t minus eta. How is that the same as doing it on the first one? I don't get it, right? Let's do it. Let's try to check it. Let's prove it. F star g is this thing, and g star f is this other thing, right? They swap roles. I put the g before just for clarity, but of course you can put them the f first and the g second. And the important thing is who has the argument. Here f has the eta, here f has the t minus eta, here g has the t minus eta, and here g has the eta. Okay, so this is the other order in the product. Let's prove that these two things are equal. Of course, this one, let me just write, again, to smash it so many times, let me just write this as, reorder it like f t minus eta prime, g eta prime, d eta prime is a dummy variable. Okay, so I can write it. All right, let's work on this one. I'm gonna do a change of variables here. Here I'm gonna do the change of variables. Eta prime is t minus eta, which of course means that eta is t minus eta prime, right? And that means also that the eta is equal to minus the eta prime. Maybe I shouldn't write it there, right? Because I'm going to write on top. Let me write here. The eta is equal to minus the eta prime. All right, let's do the change of variables. Now we need to change the limits. For a constant t, when eta goes to minus infinity, eta prime goes to plus infinity, because there's a minus. So this is a plus infinity. This is a plus infinity. When eta goes to infinity, eta prime goes to minus infinity. All right. Now I get a minus the eta prime, because the eta is minus the eta prime. And now I get f of eta is t minus eta prime, and g is g of directly eta prime. Nice. Now, I can swap the limits of the integral. I can use this, that integral AB of f of t dt is equal to minus the integral dA ft dt. If I use that, then I swap the limits, I change the sign, and I get integral minus infinity to infinity d eta prime f of t minus eta prime g eta prime. And there you go, this thing is exactly g star f of t. So yes, the convolution product is commutative. But it's an eta prime here, well, and so it's here. And I can change that back to eta if I want. It's a dummy variable, I can call it Joshua, as long as I'm consistent with what I'm doing. And I am. Alright, you see, doing these steps, I could express it as an integral. So the point is, I express it as an integral from minus infinity to infinity of dummy variable ft minus dummy variable g dummy variable. And the dummy variable takes values from infinity to infinity, exactly the same as here. So on point. Wonderful, the convolution is commutative. Alright, so what kind of things can we do now with the Laplace transform and the convolution? Let's see it. Alright, to see that, step number one is to define a new concept, which we have talked about already, is the definition of causal function. A causal function is a function that is zero for the negative values of the argument. Okay? For example, the Heaviside function, or any function multiplied by the Heaviside of t, right? Because that means that the function, so it's a function that whenever presented, right, is strictly zero here, and in the positive can do whatever. But in the negatives is zero. That's a causal function. Remember that when we talked about the Laplace transform and we said what the function does in the negative domain, it doesn't affect the Laplace transform because it's killed, right? So we're talking about the class of causal functions. But this is what a causal function is formally defined. A function that is zero for all negative values of its argument. Now, the convolution for causal we will use causal functions here for Laplace for obvious reasons because the Laplace cuts at zero. When we see it in Fourier, we won't have to work with them. But for now, let's do it with Laplace. Let's introduce the convolution of two causal functions. So now, f star g of t, let's just write the full definition, minus infinity to infinity, f of eta, g of t minus eta, d eta, right? Now, if f of eta is causal, right, that means that is zero for negative values of eta, I can remove from the integral all the negative values. So using that f of eta is causal, I get f of eta in four causal functions, just to remark it. Using, if f of eta is causal, I got this. I got f of eta 0 to infinity, g t minus eta d eta. But if g of eta is causal as well, all right, so g, when eta is too large, will be 0. So going to infinity is too much. When eta overcomes the t, it will be 0. So in fact, it will only be non-zero when the argument is positive, and the argument is positive only until eta is larger than t. The moment that eta is larger than t, is positive and larger than t, the argument becomes negative, and then the function is 0. So it's only non-zero up to eta equals t. So that allows me to do 0 to t. I'll crop the integral there as well. F of eta g of t minus eta d eta. Alright, so you see that for causal functions, the convolution of the two causal functions gets simplified. The limits, instead of going from minus infinity to infinity, they go from 0 to infinity. 0 using that f is causal, and to t instead of infinity using that g is causal. Alright? Alright, so with that, let's prove what we call the convolution theorem for the Laplace transform. The theorem, the convolution theorem for the Laplace transform, tells us that the Laplace transform of the convolution of two causal functions is the product of the Laplace transforms. Basically, Laplace transform of the convolution of f asterisk g, or f star g, it's equal to Laplace of f times, this is the regular product, the multiplication, times the Laplace of g of t. Of course, if g and f are both causal, which means there's 0 for negative t, negative values of the argument. All right, this is a very useful theorem. We will see how useful it is with an example in a second to do an inverse Laplace transform and to solve an integral equation. All right, let's prove it. The nice thing, you don't have to trust me. This is the theorem, but you don't have to trust me because we're going to prove it. You're going to be able to see it yourself. Now, what do I have here? I have the Laplace transform of the convolution of f and g, right? Of f star g. Now, remember, definition of Laplace transform, integral from 0 to infinity, exponential of minus st of the function you want to transform, dt. And the function you want to transform is the convolution, and I put in the definition of the convolution integral. Now, very important. I'm doing nothing from here to here, I'm just switching to the adult notation. And what is that? This is the notation that everybody uses for multivariable calculus when they've done and they have to do many times. For me, I know this is gonna feel outrageous to you if I write, you like this, you don't like this. For this is outrageous. For you, I'm actually expecting that you find it outrageous. However, first, that kind of teaches you about subjectivity. You know what is outrageous for me? That one. It is outrageous. And I've been doing it the whole course. I mean, it's not that outrageous. But what I mean is that this is what you do up to first year or so. And if you don't get into like STEM math heavy science. This one is super convenient for multivariable calculus because it allows you to put the limits next to the variable there are limits for integration. Now also, it can be argued that the differential belongs with the integral. The integral does not make sense without the differential. It's what gives you the sum over some values thing, you know? So yeah, there's a whole field of mathematics called measure theory. Check it if you want. It's advanced math though. Huh? Measure theory that is all about this. What does it mean to integrate over sets? What does it mean to sum in general? Things like that. I would argue certainly it's more mathematically appropriate, natural, more consistent with the universe, more in equilibrium with the nature of math to write a differential first. And I know it will be outrageous for you. For now, you can take it as a recipe not to get confused. If you do multivariable calculus and you don't do it like with the adult notation, you either lost track of where the limits belong, or you have to keep adding 1,000 parentheses and it's a mess. So all that I'm doing here is saying the same thing. Integrate this over t with these limits, integrate this over eta with these limits, and this is the expression. All right? Okay, hopefully this is not too traumatizing. I think you're adult enough to be exposed to this notation. So it's time that I do it. All right. All right, so in this adult notation, all that I wrote is the same thing as here. It's exactly the same thing. Right, so the first thing I'm going to do, I'm going to use here that f is causal. Because f is causal, the integral with respect to eta can start at 0, right? And let me write it first. I'm going to start 0 to infinity, the integral with respect to eta, then 0 to infinity, the integral with respect to t. I can do that. I mean, the integrals can swap the order, no problem. They're different variables. Integrals continuous, no problem whatsoever. Okay. So I have these two things. The integral is integral. You don't need to, but whatever, it doesn't matter. You can swap them, no problem. It's the same thing, right? I mean, it's doing the same. You integrate with respect to t0 to infinity, same thing. Integrate with respect to eta minus infinity to infinity. But I use that f is causal, so it cancels all the negative values of the integral because f for negative eta will be 0 because f is causal. All right, so I have that. This is e to the minus st, f of eta, g of t minus eta. All right, for now we've used that f is causal. We haven't used that g is causal yet. We'll use it later. For now, what we're going to do is a change of variables. So let's make the change of variables. I'll write it here. We're going to go t prime goes to t minus eta. Okay? Which means that t, right, is t prime plus eta. Okay? All right. The differentials are the same, and the limits are not quite the same, and we will see in a minute. Okay? We do this change of variables. So if we do this change of variables, we get that this convolution product. Let me open the wormhole to make sure we don't get lost. Traversable wormhole. This is an Einstein-Rosen bridge. I don't know if you ever heard that, but whatever, doesn't matter. So we get this is 0 to infinity. The eta, we haven't touched the integral with respect to eta. The change of variables is just t by t prime. All right, first thing. What are the limits of integration? Let's see. When t goes to infinity, t prime also goes to infinity for any fixed value of eta. Okay? So the upper limit is infinity. When here t goes to 0, when t goes to 0, t prime goes to minus eta. So the lower limit is minus eta. Haha. dt prime. You need to first solve the integral with respect to t prime now because it contains an eta and that integrates with respect to eta. Okay. So then we get e to the minus s. Now we had a t that becomes t prime plus eta. T prime plus eta. Okay? And then we get an f of eta that doesn't change. And then a g of t prime. Correct? All right. Now we can use that g is causal. If we use that g is causal, then this becomes 0 to infinity the eta integral 0 to infinity e to the minus s t prime. Oops, sorry, I forgot. dt prime e to the minus s t prime plus eta f of eta g of t prime. Right? Because g for negative values of the argument, in this case t prime, would be 0. So the sum over all the negative values of t prime doesn't contribute. It's 0. It's multiplied by 0 for all those values. All right. Now look how wonderful this is. It's really wonderful. I can separate, for example, f of eta. F of eta can jump the integral over t prime because, you know, this is an eta, t prime, that starts moving through and faces that and says, I'm an integral integrator. Like, what do you mean? I'm not a function of t prime. So I'm sorry, sir, you can go. So f eta can jump here. So also this thing, right, is the product. This is e minus s t prime times e minus s eta, right? It's a product of two things. The e minus s eta can also jump. It's about to get out. It's like, okay, I want to get out. Oh, I'm an integral. Oh, okay, you're not a function of t prime. You can pass. Okay, cool. Right. If this exponential tries to jump, this is going to say, oh, you stay here. You have to be integrated because you're a function of t prime. But if you're not a function of t prime, you can pass. All right, you factor out those out of the integral and you get the following. 0 to infinity, the eta, e to the minus s eta, f eta times integral. So, I mean, I'm not going to write the parentheses for now. Just, I want it to be the shock. I already did spoilers, whatever. Okay, so integral from 0 to infinity dt prime e to the minus s t prime g of t prime. And look, this thing does not depend on eta at all. So it's a constant. It doesn't have to be integrated it's a constant with respect to eta, right? So it doesn't have to be integrated at all. In fact, all these are dummy variables. The only variable that is left is s, as it should be, because we're doing our Laplace transform. There's no variables here, t prime or eta, right? They're dummy variables, all of them. So this thing is the product of two things, but you will recognize this as the Laplace transform of f of t, right? And you would say, no, that's the Laplace transform of f of eta. And I would be like, no, that's a dummy variable, right? So if it's a dummy variable, it doesn't matter. I can call it, let me do the change of variables, eta equals t. See what I mean? It's a dummy variable. I can call it Joshua. This is the Laplace transform of f of t. It's not a function of t or eta or anything. It's a function of s. All right? If you have questions about that, please come and talk to me. Okay, that's super important and it's really slammed. By this point and the number of times that I repeated it, I think it would be slammed already, right? But if not, please, let's talk. This is really important, understanding integrals properly. Now, this is also the Laplace transform of something, of g of t. You see, oh, the Laplace transform of g of t prime, and I'll be like, again, not really, no. If you don't get it, it's okay. Please talk to me. This is important. This is something that confuses many people. So it's not to be underestimated at all. It's not a stupid mistake or anything. It's something to be aware of, okay? So let's talk about it, if there's questions about it. The cool point though, is that what we got is the product of the Laplace transform of f of t times the Laplace transform of g of t, or g of Joshua, or whatever you want, right? The whole point is that we've proven the theorem. We've proven the theorem because the theorem says that the Laplace of the convolution is the product of Laplaces. Laplace of the convolution, product of Laplaces, theorem proved. And once you prove the theorem, you don't have to believe me, okay? I become irrelevant for this. Math speaks for itself to your brains, and the understanding of the universe becomes revealed, and I get like completely dwarfed by it because I'm irrelevant. Math is here for you to see. I just wrote it, and once it's written, math, gets lit and it's bright, and you get it, and everything's wonderful, and you start enjoying your lives again. Anyway, jokes aside, convolution theorem for the Laplace transform of two causal functions proven. Let's apply it to two things. We're going to use it to do an inverse Laplace transform that, as you know, is useful to solve differential equations, and we will see that because the next video is going to be about examples of application of Laplace transforms. So let's actually do a couple of applications of this theorem, and then we end the video, and the next time we do 1,000 examples. Let's do it. Okay, so the exercise is find the inverse Laplace transform of this function. I give you a function f of s and ask you to find the inverse Laplace transform. We're going to do it two methods. The method that we learned, simple fraction decomposition, and then we'll do it with the convolution theorem. All right? Let's see. So the method that through simple fraction decomposition. Okay, we can solve it through simple fraction decomposition. F of s is that. I'm not going to do the full decomposition. You should be able to know how to do it by now. There's a whole video about doing them with several examples. There is also one more that I did for the Laplace transform. In many cases, I will not be doing them. I really want you to practice them, okay? I don't want to spend a long video time doing that. But this is easy, no? The roots, so this thing is a divided by s squared times s squared plus a. So there are two simple fractions if you want, that you can write a plus b s s squared, and the other fraction would be c plus d s squared plus a, right? And then you find the coefficients, common factor, this will be multiplied by s squared, this will be multiplied by s squared plus a, and you equate, the denominators are the same, and you equate all the powers on both sides, and you can tell quickly that b and d are going to be 0, only a and c are going to be non-zero, and so on and so forth. The result, after doing the steps, is 1 over a, 1 over s squared, plus or minus 1 over a, 1 over a squared plus x squared. That's a very simple system of equations. Two unknowns, two equations, very simple, and you get that. All right, wonderful. So we want the inverse Laplace transform of that. So we know now that small f of t would be equal to the inverse Laplace of capital F of s, which would be equal, wormhole opening, incoming wormhole here. That thing would be equal to, because of linearity, right, 1 over a inverse Laplace of 1 over s squared minus 1 over a inverse Laplace of, there we go, 1 over a squared plus s squared. Now, these two functions are very similar to two Laplace transforms that we learned how to do. Remember, the Laplace transform of t is 1 over s squared. That means the inverse Laplace transform of 1 over s squared is t. The Laplace transform of the sine is a divided by a squared plus a squared. So the inverse Laplace of a divided by a squared plus a squared is the sine. So all that we need to do is to play a tiny bit, manipulate slightly this so they look like that one. Actually, the first term is very easy. The first term I'm going to leave it as is. 1 over a, it's already t, right? It's the inverse Laplace transform of that. Minus, now this one is not quite that, but we can make it that very easily. Let's keep the 1 over a. And what I'm going to do is I'm going to multiply by a and divide by a. Divide by a outside, multiply by a inside. So if I do that, I would get 1 over a outside, inverse Laplace of a squared plus s squared, right? Linearity of the Laplace tells me that these a's cancel. But now it looks like the sine, like the Laplace transform of the sine, so that means that this is equal to t over a minus 1 over a sine of a t. Okay, square, like that. 1 over a square, right? 1 over a times 1 over a. All right, and that is f of t. And that solves the problem. That's the inverse Laplace transform. The only difficulty of that, well, there are two difficulties if you want, that we will always face, right? Find the simple fraction decomposition. That's not too difficult, it's very algorithmic. And then after that, recognize what you have in terms of things that you know how to solve the Laplace transform, inverse. And if it's not looking like that, morph it, multiply and divide by things so that it looks like one of those. Alrighty, let's do it with the convolution theorem. So another way of doing it is I know that L, so let's see if it, I think it fits, yeah. Let's do it here without erasing. So f of s, maybe I'll write it here. The Laplace transform inverse of f of s is equal to the Laplace transform inverse. Let me copy the full function that I have over there. A divided by s to the 4th power plus a square s square. Right. But that thing is the product of two things, right? This is the inverse Laplace of 1 over s, right, square times a over s squared plus a squared, no? Oh, that's nice. So it's the product of two Laplace transforms, right? So this thing is the inverse Laplace of the Laplace of t, which is 1 over s squared, times the Laplace of sine of at, which is a over s squared divided by a squared. Nice. So that thing, actually, the convolution theorem, remember the convolution theorem for the Laplace tells me, again, knowing that they have to be causal functions in order to have the Laplace, because they have to be removable negative parts. The Laplace transform removes the negative parts, so these are certainly causal functions. So what we have here is that L of, so the convolution theorem told me that f star g of t is equal to Laplace of f times Laplace of g. So I can read this backwards and say, oh, this thing is the inverse Laplace of the convolution, so the Laplace transform of the convolution of f, in this case is t star sine of at. Right? And the inverse Laplace and the Laplace now cancel. Here they don't cancel because a product and the Laplace is linear, it doesn't cancel. Here they cancel. And all that I'm left with is that the result is the inverse Laplace transform of f of s is literally the convolution of t with the sine of at. So all that is left to do is do that product. So this is equal to, then I'll write it again, t convolution sine of at. And that is equal to the integral from 0 to t remember, it's minus infinity to infinity, but the two functions are causal functions, so it becomes 0 to t for the Laplace transform of d eta. At those notation, why not? Sine a eta t minus eta. Alright, so if I do this integral that you can do by parts, it's not a difficult integral to do by parts. It's a bit more difficult this time to do with Feynman's trick. By parts is slightly faster for this one. Still, if you do it, what you get is at minus sine at a squared. There are several methods to do these integrals. Integration by parts, Feynman's trick with a bit of cleverness here. Wolfram alpha, yes, you're allowed to use Wolfram alpha to check your integrals, but you better know how to solve them. There's not going to be exams, so I have no means to know if you don't know your integrals for Wolfram alpha. So I appeal to your sense of honor and math. Please learn how to do your integrals, okay? Anyway, this is the result, and this is the same result. If you factor this into terms, it's exactly this, right? Let's just write it. This is the same as t over a, the a cancels with the a squared, minus 1 over a squared sine of at. So it's the same thing if we do it with the convolution theorem. I guess one of the questions that you may have, that is beyond calculational stuff, is, hold on, but this theorem for the Laplace only works for causal functions, and t and the sine are not causal functions. Yes, they are. Because we're inverting a Laplace transform, that means that originally, even if you had a full sine in the whole domain, or a full t in the whole domain, the Laplace transform already killed the negative part. You see? We could have taken the heavy side. That's the integral starts from 0, so it's multiplied by the heavy side. This is one of the things that I talked about at the beginning of the blog, but I think we're getting a little bit more understanding of why the Laplace transform really ignores everything that happens in the negative and sets it as if it were 0. All right, so it kind of applies to causal functions already. Once you go through the Laplace transform, you're a causal function. Anyway, we'll talk more about that when we talk about stability and so on. All right, if you have questions, please bring them on Friday. On Friday, I always say on Friday. Bring them into our discussion sessions. There's one on Fridays and every other week on Mondays. All right? Okay, cool. So we've seen that the convolution theorem can be used to compute Laplace transforms as an integral, inverse Laplace transforms, rather than use simple fraction decomposition. Now, in some cases, of course. Now, let's use it to solve the last thing we're going to do in this video. Let's use the convolution theorem to solve an integral equation. That should be fun. Alright, the exercise we're going to solve is x of t plus integral of 0 to t minus tau x tau d tau equals the sine of 2t. So that kind of equations actually do appear in signal processing related to autocorrelation functions, although here we just let's solve it as an exercise. First thing that we realize is that this thing is the convolution product of the causal version of t and the causal version of x of t. Right? This is the convolution integral when the functions are causal. So, assuming that x of t would be a causal function, we're going to be able to solve that. Kind of makes sense for signals, because for signals you start at some time, and you call that time t equals 0. Anyways, so let's solve the equation. How do we solve the equation? Well, the same way we solve different. You see, this is an integral equation, because instead of derivatives of x, I have integrals of x. Alright, so to solve this equation, let's take Laplace transforms. If we take Laplace transform, we get, by linearity of course, the Laplace transform of x of t plus the Laplace transform of the convolution of t and x of t equals the Laplace transform of the sine of 2t. Now, I did write all the Laplace transforms that we're going to need here. The Laplace transform of the sine is a over s squared divided plus a squared. The Laplace transform of t is 1 over s squared. The Laplace transform of the cosine is s divided by s squared plus a squared. Notice that I notated instead of having Laplace transform of cos equals that, I have the Laplace inverse equals the cos, which is the same. Alright then, so the Laplace transform of x, we call it capital X of x. Now plus, oh, nice. This is the Laplace transform of the convolution of two functions. So the Laplace transform of t star x of t would be equal, because it's a convolution, right? Let me just put the full notation, just to be consistent with it. Right? The Laplace transform of the convolution, it's equal to the product of the Laplace transforms of the functions, right? Well, that's nice. The Laplace transform of t is 1 over s squared times capital X of s. Very nice, that is this. Right? And this thing, it's equal to the Laplace transform of the sine of 2t, and the Laplace transform of the sine of 2t is just 2, that's a, divided by s squared plus 2 squared, which is 4. So that means, let's just write it, that 1 over s squared plus 1 multiplying capital X, it's equal to 2 s squared plus 4. This thing, well, let's just write it, s squared plus 1 divided by s squared x, right, of s, right, this is of s. I mean, maybe I don't have to write it, but I write it just for clarity, equals 2 s squared plus 4. And let me pull the s squared here, the s squared plus 1 here, and let me factor it like this. This means that capital X of s, it's equal to, and I'm going to write it as twice s times s squared plus 4 times s squared plus 1. I just wrote it like that. You see, I have this times that, this is here. I have an s squared here that I wrote as s times s, and then the factor 2 in here. Why do I write it like that? Because I realized that these two things are Laplace transforms of cosines. That's why I wrote them like that. So, if we continue, what we get is that I'll just copy here the result. X of s is equal to twice s divided by s squared plus 4, and then s divided by s squared plus 1. All right. Now I need to take inverse Laplace transforms. So I know that x of t would be the inverse Laplace of capital X of s. All right. And that is the inverse Laplace of the two factors out, and I have s divided by s squared plus 4 times s divided by s squared plus 1. I could do common simple fractions, but now that we're with the convolution theorem, we already used the convolution theorem here, might as well use it to solve the inverse Laplace transform. Let's do it. So I have the product of this thing. I realized that this is twice the Laplace inverse of the Laplace transform of this thing is the Laplace transform of the cosine when a is equal to 2. So this is the Laplace transform of cosine of 2t. And this thing is the Laplace transform of the cosine of t. Right? Just check the formulas. A is equal to 2 in this one. A is equal to 1 in this one. Wonderful. So that means that I have the inverse Laplace of the product of two Laplaces, but I can use the convolution theorem to say, well, maybe write an arrow, wormhole, and then a wormhole, incoming wormhole, and an arrow, and that means that x of t, now we have is equal to twice the inverse Laplace transform of the Laplace transform of the convolution of the cosine of 2t and the cosine of t. The inverse Laplace cancels. All that I'm left with is that x of t is twice the convolution of the cosine of 2t and the cosine of t. Alright, all that is left is to solve that convolution integral. So this is equal to, this is right here, twice integral 0 to t cosine of 2t cosine of t minus eta, the eta, which is, this is an integral that you can do by parts, but I'll give it to you to do it. The final result is 1 over 3, 4 times the sine of 2t minus the sine of t. and that is x of t. All right, so please complete doing the integral. This is the irrelevant part, doing the integral. You can also solve it using partial fraction decomposition and check that you have the same, okay? Now, super interesting. We found the solution, which is a function that satisfies this equation that seems tough as hell. This is really a tough equation. Look at that. We solved it with the convolution theorem. So hopefully you've seen the power of it. You won't have to do many of this. This is more just to see the power. In assignments and so on, I won't probably ask you to solve many, maybe one integral equation, but it's going to be mostly differential equations. All right, that's all for today. I hope that you realize the power of the convolution theorem, and at the very least that you've learned very well what is the convolution. It will reappear in Fourier transforms. It will reappear in your signal processing and all your life. And in the next video, we're going to practice using the Laplace transform to solve differential equations. We're going to do a bunch of examples. That's it for today. See you then.